This is Physics 2211 Lab 3 Black Hole in Orbits by William Barron. The purpose of this lab is to use a computational model in GlowScript to predict and visualize the motion of objects in space. In Part 1, we will simulate the motion of a star as it orbits a black hole, and in Part 2, we will simulate the orbit of a spaceship as it travels around the moon orbiting a planet. Now, this should result in two models that show how each model is affected in its respective system. Fundamental physics principles. Using Newton's second law, we can find the position and velocity update formulas shown on the left. The total net force we can also find, which is equal to F net parallel plus F net perpendicular, which are shown on the left. Also, we should know that F net perpendicular is equal to the centrifugal force, or mv squared over r. Now lastly, we have the law of gravitation, which is represented by F equals gmm over r squared. Now we will use these formulas throughout our code so that we can solve for the unknowns. Part 1, the mass of the black hole. The initial conditions were that the mass of the star is 2.0 times 10 to the 30 kilograms. The mass of the black hole is unknown, and its location is at the origin. Now this is the code that we use to find the mass of the black hole, and also F net parallel, and F net perpendicular. And it was done using the formulas previously shown. Part 1 results. The mass of the black hole is 1.07555 e to the 34 kilograms. The magnitude of F net is 7.9 e to the 28 newtons. F net parallel is 3.37 e to the 27 newtons, and F net perpendicular is 7.9 e to the 28 newtons. What does this mean? The net force represents the gravitational pull on the star at each moment, while the rate of change of momentum shows how the star's motion actually changes. Now the parallel component affects the star's speed, while the perpendicular component changes its direction. Part 2, the initial velocity for the spaceship. Using the formulas that were previously shown earlier, we need to use them to find the initial velocity of the spaceship so that we can make the figure 8 orbit. Now this will be done through trial and error. Now I ended up using the vector negative 24,000, 24,310, and 0 as the closest velocity where the spaceship was affected by both the planet and the moon. Part 2 results. As you can see in the image, I was not able to find a velocity for the ship in order for it to make the figure 8 pattern. Now even though a figure 8 pattern was not made, the velocity that I chose shows that the motion of the ship was influenced by both the moon and its planet, which is shown by its elliptical orbit. What if? If this imaginary system had a black hole, a star, a planet, and a moon, now the computational model would need to include the gravitational forces between every object. The dominant force would come from the black hole since it's the largest mass and therefore has the strongest gravitational force. Now since the star has the next largest mass, it would be affected by the black hole, but also have an effect on the planet and the moon. And while the planet and the moon would mainly interact with each other and have a much smaller effect on the star or black hole. Possible errors. The possible errors that could have occurred are minimal due to this lab being purely computational. With that being said, there could have been mistyped formulas or inputs. And also, since trial and error was used for the ship's velocity in Part 2, a more accurate velocity could result in a better figure 8 pattern than I was able to find. So in conclusion, we were able to find the mass of the black hole, as well as the initial velocity for the spaceship to orbit both the moon and the planet.